Hello, everybody, and welcome back to another Mr. Farney Earth Science video. Here we are in the second section of our meteorology unit, weather. In this video, we're going to focus on two different things. We're going to focus a little bit on causes of weather, focusing in on what are referred to as air masses. And then the second section of this video, we're going to get a little more specific about different types of wind, how kind of wind moves in the northern hemisphere, the main drivers behind that, a little bit of information about different types of storm fronts right before the next video where we actually start transitioning into looking at different types of weather maps. So the big idea of this entire section known as weather is that weather patterns can be observed. We can analyze the data that we took from our observations, both qualitative and quantitatively, and then based upon our observations and our analysis, we can then begin to make predictions. That's the big idea of the meteorology section. The first little chunk of this is our causes of weather. And the main idea here is talking about these things called air masses that are found all around the world. Each of them have their own specific qualities as far as temperature and moisture levels go. And because of these differences in temperature and moisture, we can begin, getting a little bit of movement of air, because remember, wind moves from differences in temperature, because that temperature causing differences in pressure because of this uneven heating of the earth. Now, before we get too much into that, we want to make sure that we understand the difference between weather and climate. Weather is short term. It's a very short period of time. It can be minutes, hours, days. It's what's happening outside and how it's changing very quickly as far as weather goes, as far as atmospheric conditions like temperature and dew point and pressure and wind, cloud cover, all those things is weather, short term. Climate are those things, but it's the averages of those things over decades. Generally 30 years worth of time are our climate cycles, where we can then go back and analyze how one climate cycle is different from another, how kind of one chunk of 30 years is different from the next chunk. And then we can analyze these climate trends to see how climate is changing over a long period of time. So it's important to recognize early on that weather is short term and climate is long-term change. Now, back to this uneven heating of the Earth's surface that kind of triggers all these different processes. We have to talk about that the Earth is tilted. It's not straight up and down on its axis. It's tilted at 23.5 degrees. And we'll come back to that in our astronomy unit. The angle at which the sun hits the Earth is not constant all the way from the poles to the equator. And because of this tilt, we have that uneven heating of the Earth's surface, which gives us all these different temperature changes, which then which adjusts the air pressure. So the angle at which these rays hit the Earth is called the angle of insolation. Here are kind of 5 main points that the angle of insolation causes. First thing is the poles receive less light. Second, the equator gets more direct light and more concentrated light. So it's going to be warmer. It's going to absorb more energy. 3, the poles, if they do receive light, it's going to spread out that concentration, so it's not absorbing as much. And then because we have all these temperature differences around the world, we're going to get air movement beginning to happen in the form of wind. We'll get this thing called jet streams that we'll talk about in a little later of a video, and then storm formation because of this uneven heating of the Earth's surface. We then begin to develop these really large air masses that can be hundreds or thousands of miles big. And they're all generally categorized based on what their temperature is and how much moisture they contain or what their humidity is. These air masses, wherever they form, they're going to maintain the properties of the area in which they formed. And we call that area the source region. So there are several different air masses that we're going to concern ourselves with. Here are what we refer to as the big 5. We have the Arctic air mass that's very cold and very dry. We have the continental polar air mass that is cold and dry. And we have the continental tropical air mass that's hot and dry. So this first 3 are all going to be very dry. If they form over a continent, there's not enough water on that continent for it to kind of take in to make it be very humid. For that, you need to go over the ocean, or our last 2. The word maritime means ocean. So maritime polar is mild and humid. It's formed further up north in our oceans, compared to maritime tropical, which is found closer to the equator. It's going to be much more hot, much more humid. So wherever these air masses form, and they're symbolized by these abbreviated either 1 or 2 letter symbols on weather maps, wherever they form, they're going to maintain the characteristics of that area. So on this map, you can see our Arctic, our maritime polars, and our continental polar. Those are colder ones, quote unquote, because they're formed more north, closer to the poles, whereas our tropical ones, they're formed further south, closer to the equator, where it is generally warmer. Here's another map that kind of shows them all together, and generally the regions of the United States that they're going to affect. That's indicated by their arrows there. This is another map that shows these air masses kind of interacting with each other, the direction that they're going to go, and then we have these kind of fronts that are going to separate primarily these different areas from each other. But it's good to note that these are not static locations. They can move, they can adjust depending how the other ones are being influenced by kind of wind speed, by the adjustment of heat, depending where the Earth is in relationship to the sun during its kind of orbit around it. We'll come back and talk more about that in astronomy, but just know for now, these air masses, they're not going to perfectly stay in these exact spots year round. With those air masses in plates, depending how they move with different pressures, we can see changes in pressures and temperatures. They can move, they can change, they can collide with one another. And due to those interactions, we get these 3 major wind systems to begin kind of popping up and causing different things from happening. So the first one are polar easterlies. These are kind of a wind system where you have cold, dense air that's going to sink toward the poles. And because of that, it's going to kind of generate some wind coming in from the eastward direction. Prevailing westerlies, this is the one that we deal with here in the United States. We see these in the northern hemisphere and the southern hemisphere, but it's the prevailing westerlies that is the reason why we have weather moving from west to east in the United States, because we have this generally westward way movement of kind of this upper level wind. And then we also have the trade winds, which are kind of found closer to the central latitude wind systems, kind of around 30 north, 30 south, that kind of move in the opposite direction of the prevailing westerlies. We also have these pressure belts that kind of come into play. 30 north, 30 south, we have the sinking air, not a lot of wind movement with this, called the horse latitudes. And then one that's very important, the intertropical convergence zone, or the ITCZ, which is found near the equator. It has a lot of low pressure. It creates some rising air with it. And we know from our lesson that if we have rising warm air in that area, we are going to start seeing a lot of precipitation, the development of thunderstorms, and it's near the ITCZ that we see the development of rainforests. Now, it's the interaction between these pressure belts and these wind systems, along with the Earth's rotation, that generates what we call the Coriolis effect, which is why wind moves certain directions in the northern hemisphere compared to the southern hemisphere. It takes all these things into account. This YouTube video that's on the note slides here, I encourage you to watch. It's about 2 minutes long, and it goes more in depth about the Coriolis effect. And it puts all these things on this picture here into a context that will make more sense to you. Again, here's a much simpler version that kind of shows the direction of the polar easterlies, where we have kind of that sinking air. The westerlies, we have the rising air a little bit that gives us our precipitation. Trade winds, you get a little bit of like rising and sinking air at different parts and locations here. So this map is very good, kind of just very basic understanding of where do we have sinking air, where do we have rising air going on here. With all that said, we're going to just briefly go through 4 different types of storm fronts here. And this is just interaction of cold air and warm air. What are they doing? A cold front is when you have an area of cold sinking air coming in, and it's going to kind of wedge underneath warm air. So cold air is coming in, it's going to kind of almost act like a snow plow and push warm air up over top of it. That's the first one. Kind of looks like this picture here. Cold air comes in, pushes warm air above it. As that warm air rises, clouds condense, we get rain. That's how cold fronts work. Warm fronts It's when you have warm air, it's going to kind of wedge on top of and slowly push out the cold air that's already in place. Again, works very similar as that warm air kind of rises on top of a cold area. That moisture is going to rise, it's going to condense, and we're going to get rain. So in a cold front, just to kind of compare the two, cold front is wedging warm air on top of it, whereas a warm front, you're going to lay that warm air on top of cold air. It's kind of flipped. Then we have two kind of special fronts that come past that. A stationary front where cold air and warm air meet and nobody's really winning that situation. Cold air is not pushing the wind forward. The warm air is just kind of holding off that cold air. We have a stationary front. It just gets cloudy, but it's not enough force from the cold air to force moisture up over top of it for it to start precipitating. Then we get an occluded front when you have very fast cold moving air that is coming behind kind of slower moving cold air, and it kind of wedges warm air on top of it in kind of this weird pocket, this occluded front. And when this happens, you get this kind of moist air cloud development kind of in the section of it, but you're not necessarily going to get too much precipitation from this. The big thing with occluded fronts, it's kind of like cold air coming into cold air, but one section of cold air is moving slower. It's like when you're driving on the highway and you get in the fast lane and somebody's going very slow in the fast lane, and then you get kind of stuck behind it. That's what's going on here with an occluded front. Weather maps can show us high and low pressure systems. High means good weather because it's sinking cooler air. Low means bad weather because it's rising warm air. So on weather maps, H's mean good, fair weather, high pressure. Low pressure is signified by an L, or that's our rising warm air that's going to condense and give us rain. So it's important to be able to distinguish between high and low pressure systems on weather maps. Here's the last thing just to mention. Again, high pressure, it will rotate clockwise or to the right in the northern hemisphere. You have sinking air with this. Nice weather, good air pressures, sunny days. Low pressure, it's all the opposite. You have air that's rising, you're rotating counterclockwise or to the left, you're going to get rain, you're going to get clouds, and you're going to get some lower pressure developments. So I know I threw a ton of stuff at you in this video, and I encourage you to go back and view it again. But these are all just kind of weather basics before we move into what we're going to talk about in the next video, how we actually can go about and start collecting different weather data that start to build a picture of what's going on currently with our weather, and then what's going to happen, let's say, in the next hour, several days, or even a week out. So thank you for being patient watching through this video. If you have any questions for me, do not hesitate to ask. If not, have a good rest of your day, and we will see you next time. Bye-bye.